All right, let's dive into something that sounds like it's straight out of science fiction, but is becoming very, very real. We're talking about two technologies that are literally changing the world as we speak: artificial intelligence and, get this, nuclear fusion. This isn't just some cool academic idea. It's quickly becoming the answer to one of the biggest problems we're about to face.
So, let's start with this number, 50 gigawatt hours. What is that? Well, that is the absolutely insane amount of energy it takes to train just one of today's top AI models. To give you an idea of what that means, that's enough juice to power over 4,000 American homes for an entire year, all for a single training run.
And believe me, it is not stopping there. The AI models coming down the pipe are expected to need 100, maybe even 1,000 times more energy than that. This crazy growth is creating what a lot of people are calling the grid gap. Our power grid, the infrastructure we rely on, it just wasn't designed for this kind of massive, focused demand.
Okay, so let's break down this problem. These new AI data centers are becoming gigantic, needing 1 to 2 gigawatts of power. And if you want to build one, the waiting list just to connect to the grid can be 5, even 10 years long. And look, solar and wind are fantastic, but they have an issue. They don't work when the sun isn't shining or the wind isn't blowing. AI's hardware, on the other hand, needs what's called baseload power. That means a constant, steady, 24/7 flow of electricity, no interruptions. So, where on earth do you get that kind of clean, reliable power? Well, the solution is pretty mind-blowing.
The solution might just be nuclear fusion. Yeah, you heard that right. We're talking about building a star on Earth, recreating the exact same process that powers our sun to solve AI's gigantic energy problem. It is, quite literally, the ultimate power source.
So what even is fusion? Well, you've probably heard of nuclear fission, right? That's where we split big, heavy atoms apart. Fusion is the complete opposite. We take two super light atoms and smash them together so hard they fuse into one. Now here's the magic. The new atom that's created is just a tiny, tiny bit lighter than the two that went in. And that little bit of lost mass, it hasn't disappeared. It gets converted into a huge amount of pure energy, thanks to Einstein's famous equation, E equals mc squared.
And the fuel for this whole thing is just elegant. You start with deuterium, which is basically a heavy type of hydrogen that you can get from plain old seawater. You add something called tritium, which the reactor can actually make for itself using lithium. You fuse them under insane conditions, and what comes out the other side? Harmless helium, yeah, the stuff you put in balloons, and an absolutely enormous blast of clean energy. The fuel is everywhere. It's practically inexhaustible.
So how do you actually make a star in a box? Well, scientists have a name for it, the Lawson Criterion. But you can just think of it as a recipe, and you need all three ingredients at the exact same time. First, you need insane temperatures. We're talking 150 million degrees Celsius. That's 10 times hotter than the center of the sun. Second, you need a high density of fuel so the particles are close enough to actually hit each other. And third, you have to hold it all together long enough for the fusion reaction to get going and sustain itself. Easy, right?
Yeah, not so easy. Pulling off that recipe is one of the greatest engineering challenges humanity has ever faced. But brilliant teams all over the world are tackling it, and they're using a few different approaches. Let's take a look at the 4 main flavors of fusion being worked on right now.
Okay, so you've got 4 main contenders. First is the Tokamak, which uses powerful magnets to hold the superheated gas, or plasma, in a donut shape. It's the most developed tech out there. Then there's the Stellarator. It's like a Tokamak, but the magnetic cage is twisted into this wild, complex shape that's naturally more stable. A completely different idea is laser inertial fusion. This is so cool. You blast a tiny little pellet of fuel with the most powerful lasers on Earth, crushing it until it fuses. And this one's a big deal because it's already proven it can get more energy out than it puts in, a net energy gain. Finally, there's FRC, which shoots these little plasma smoke rings at each other. It's a really clever design that could lead to much smaller reactors.
But here is where the story gets really wild. This isn't just a one-way street where AI is the hungry customer and fusion is the power plant. No, it's a virtuous cycle. These two revolutionary technologies are actually helping each other grow, and they're doing it right now.
I mean, look at this. AI is helping solve some of fusion's oldest, most difficult problems. That super hot, chaotic plasma, AI can actually predict its behavior and control it in real time, something no human could ever do. AI is also running millions of simulations to invent brand new materials that can survive the extreme heat inside a reactor. And it's creating digital twins, perfect virtual copies of reactors, to test and optimize designs before anyone even starts building.
And in return, Fusion gives AI everything it could possibly want. Its energy density is just staggering, 4 million times more powerful than coal. The fuel is cheap and stable, so AI companies don't have to worry about wild swings in energy prices. And most importantly, it delivers that clean, reliable, 24/7 baseload power that these massive data centers desperately need. It's the perfect power source for the future of intelligence.
So, I know what you're thinking. This all sounds amazing, but isn't fusion always 50 years away? That's been the joke for decades, right? Well, for the first time in history, the answer is a clear and simple no. This isn't a distant dream anymore. We're talking about a 2030s reality.
So here's the roadmap. Right now, we're in what's called the proof era. We're seeing all the key tech demonstrations succeed. By 2028, we're expecting the very first commercial power agreement to be fulfilled. Then in the early 2030s, we hit the pilot phase. That's when the first fusion plants will actually start connecting to the grid. And from 2040 onward, the plan is to scale up and start mass producing these reactors for the world.
And this is not just some hopeful projection on a PowerPoint slide. This is actually happening. Microsoft, one of the biggest AI companies on the planet, has already signed a real, historic deal with a fusion company called Helion. They've agreed to buy 50 megawatts of fusion power, starting in 2028. This is the first deal of its kind, and it's a massive, massive vote of confidence.
Okay, so let's tackle the elephant in the room. When people hear the word nuclear, their minds immediately go to the fission power plants we have today. And it's so important to understand that fusion is a completely different animal. It is fundamentally safer and cleaner.
Let's just put them side by side. Fission splits big, heavy, and rare atoms. It creates that nasty radioactive waste that stays dangerous for thousands of years, and there's always that small but real risk of a meltdown. Fusion, on the other hand, fuses tiny, abundant atoms. It creates zero high-level long-term waste. And, most importantly, it is inherently safe. If anything at all goes wrong, the reaction just stops. It fizzles out. A meltdown is physically impossible.
Now, that's not to say it's all smooth sailing from here. Of course not. There are still some pretty big hurdles to clear. But these are engineering problems, not physics problems. We know it can work. They need to get the reactors to breathe their own tritium fuel efficiently. They need to perfect the materials that can handle the intense conditions for years on end. And yeah, the first plants are going to be expensive. They'll need to scale up manufacturing to bring the cost down. But these are all solvable problems that people are actively working on right now.
So all of this leaves us with one final, absolutely huge question. We're in this incredible race to build two technologies that will completely redefine our world. One of them, AI, has a potentially infinite appetite for energy. And the other, fusion, promises a near infinite supply of it. The question is no longer if we can do this, but can we do it in time? Will we invent the power source of the future, just in time to fuel the intelligence of the future?